Alright, this is number 6 from the 2010 Form B AP Physics B exam, and this is a fluid physics problem. We've got an object suspended from a spring scale in air, then in water, and we now are going to take the measurements from the scale when it's in the air to the one that's in the water. We know the density of the water, and we're going to figure a bunch of stuff out. So first and foremost, what's the buoyant force acting on it? Well, let's think about this. If right here it's got a weight down of 17.8 newtons, and then the only change we have now is putting it in water, and that drops to 16.2 newtons. Either it miraculously lost mass, or something was pushing up on it, and I'm pretty sure that's the thing. Something was pushing up on it. So the net force is really 16 newtons. There's still a weight of 17.8 newtons down. The buoyant force up must be the difference between those two numbers, or 1.6 newtons, to allow the overall net force to be what pulls the spring scale down. So the buoyant force for A is simply the difference between those two forces, or 1.6 newtons. B, we want to know the volume of the object. Well, if you recall, the buoyant force on any object will be equal to the density of the fluid it's in, so in this case it's going to be water, times the volume displaced of the fluid, or the volume of the object's submerged. In this case, the object is fully submerged, so I'm going to write down the volume of the object. It could have been the volume of the water displaced as well if we knew that. And then times G. Well, we already know F. We're looking for V. V of the object is therefore going to be the buoyant force acting on that object divided by the density of the fluid it's in times gravity. So this could be 1.6 newtons divided by 1,000 times the acceleration due to gravity, which I like to use as 10. That's going to give me 1.6 times 10 to the negative 4 cubic meters. 1.6 divided by 10,000. C, what is the density of the object? Well, the density of any object is going to be the mass of that object over the volume of the object. Well, we don't know the mass directly, but we do know the weight, and we know weight is mg. So we're just going to take the weight and divide by gravity. So instead of it being 17.8 newtons, 17.8 divided by 10 meters per second squared, or 1.78 kilograms. So we're dealing with 1.78 kilograms divided by the volume that we just determined of 1.6 times 10 to the negative 4 cubic meters. Let me calculate this. This is giving us an answer of 11,125 kilograms per cubic meter. Alright, and then D, how would the absolute pressure at the bottom of the water change if the object were to be removed? There's a couple different ways of answer this one. I think the one I'm going to use is the most logical. First, the pressure at the bottom is going to be equal to the force acting at the bottom divided by the area of the bottom. The area isn't changing, so that's not a problem, but the force pushing down at the bottom part here, that's definitely going to change, because in the beginning, the cup is supporting the water above it, plus the ball, plus the air above it. When we remove the object, it's only supporting the water and the air, so it's the force acting downward is decreased. It doesn't need to support it anymore. As a result of the force decreasing, the pressure needs to decrease. Or you could also relate it to the whole pressures related to rho GH. And H is the depth of the fluid, and that's going to decrease once the ball gets taken out. I like the whole supporting force bit more, but to each his own. Okay, that's it. Thank you.